The fifth and final section of the circular motion chapter, and this section is about objects not constrained on a circular path. So what we have here are objects which start on a circular path, and then for some reason they come off of that circular path. So you could imagine maybe a stone or a weight on a piece of string, and then for some reason maybe the string breaks and it doesn't follow the circular path, it comes off of that circular path. So maybe if you've got something going around like this, and let's say at this point the string breaks, and then what's going to happen is that object will now follow a normal path that we would expect where gravity is involved, like projectile motion. So let's draw something like that. Let's say that an object, when it gets to this point, it leaves the circular path, so its initial velocity is going to be like this, and then it's going to follow projectile motion. So if we draw some axes, for example, like this, we would now consider this as projectile motion, with this our x-axis and the y-axis here, and the speed at which it leaves the circular path will be our initial speed for our projectile motion. And for projectile motion, you'll remember that horizontally the speed is constant, so we can just use speed, distance and time. So speed, distance, time. The speed is going to be the horizontal component of this speed here, so we want to know this angle here, the angle at projection, and I'll show you how we can work that out in a moment. So that would be u cos theta, and we can rearrange that for t, because we'll probably want to use the t when we're looking at the vertical motion, which we'll look at in a moment. So t is going to be the distance, and that's going to be the horizontal displacement x over the initial speed u cos theta. And when we're looking at the vertical motion here, we'll just use suvat, s-u-v-a-t. There's a couple of things we can fill in here. So acceleration is going to be minus 9.8 or negative g, because our acceleration due to gravity is going to be pointing down like this. T we can take from our horizontal motion, so that'd be x over u cos theta, and u, well, that's going to be the vertical component of the initial speed as it leaves this circular path, and that is going to be u sine theta. Now I did say it's going to be possible to work out what this angle is here. So let's say, for example, that we have an object and it starts initially in this position down here, and it moves through an angle of theta and then leaves the circular path. So we'll label this as theta here. Now you can see that this line going straight up, this is also going to be theta, because we just got like alternate angles there. And then this is a right angle, so from here to here, so this velocity here is always at a tangent to this line here, which goes to the center. So here we've got a right angle, so that means that this angle at the top is going to be 90 minus theta. So this angle in here is 90 minus theta. But then we've got another right angle here, and this angle is going to be 90 minus this. In other words, 90 minus 90 minus theta, and that just leaves you a theta. So this angle here is going to be the same as this angle here. Now these questions could also be done using potential and kinetic energy, but personally I just find using suvat and projectile motions an easier way of working out what this object or particle is going to do once it leaves its circular path. Example 19. A particle P of mass m is attached to one end of a light inextensible string of length L. The other end of the string is attached to a fixed point O. The particle is hanging in equilibrium at point A, directly below O, when it is set in motion with a horizontal speed of 2 root GL. When OP has turned through an angle of theta and the string is still taut, the tension in the string is T. We've got 3 things we need to find here. I'm going to start by drawing a diagram. So this represents what's going on initially. This is where the particle ends up. So we'll need to mark on a few things. So we're going to put that it's moved through an angle of theta. We're going to be using F equals ma. So we're going to have tension pointing towards the center. We're also going to have the acceleration pointing towards the center. Now in this case, because we've been given a speed, a linear speed, that acceleration is going to be v squared over r, and r is the length of the string, the radius of the circular motion, which is L. So we'll just mark that on here and here. We'll also need to put on the weight of this object of mass m, so this is mg. And because we're going to be using F equals ma and we're going to be resolving in this direction parallel to the tension, we'll need to mark down this component of the weight, and I can mark in that this angle here is also theta, so it's corresponding to this angle here. So I will have mg cos theta for this component of the weight here. So we'll start with part A, and we need to find an expression for t. So we'll start by resolving towards the center of the circle, and we'll have t, which is pointing towards the center. Then we need to subtract mg cos theta, because that's pointing away from the circle, and that's going to equal ma. So m times by the acceleration, and the acceleration is going to be v squared over L. So we can rearrange that and write t is equal to, and we'll write this as mv squared over L plus mg cos theta. Now we want to eliminate this v squared from this equation. So this is where we're going to use conservation of energy. We're going to take this lowest point here as being 0 potential energy, and we'll work out the total energy at this point here and the total energy at this point here, and we can rearrange it for v or v squared. Right, so at the lowest point, what's the total energy? Well, there's no potential energy, that's 0, and the kinetic energy is going to be half m v squared, so that's going to be 2 root GL squared. So that's going to give us, I'll write it over here, half m, and then if we square that thing in the bracket, that'll give us 4 GL, and that's going to simplify to 2 mgl. So this is the total energy that we're going to have at the lowest point. Right, so we now want to work out the total energy at this point. So let's call it after moving through an angle of theta. So after an angle of theta, we're going to work out the total energy. So we'll start with a potential energy. So that's going to be mg times by the increase in height. Now this is similar to one that we've done before. The increase in height is going to be this part here. Let's just highlight that. So this is the increase in height, this bit here. Let's do that in another color so it's a little bit clearer. Yeah, so this is the increase in height, and that's going to be L, this total length, minus this part here, which is going to be L cos theta, if you consider this right angle triangle here. So the increase in height is going to be mg, and then we're going to times that by L minus L cos theta. So there's our potential energy. Now for our kinetic energy, it's going to be half m, and the actual speed at that point we'll call it v, so it's half mv squared. So our total energy at the lowest point is going to be equal to the total energy at this angle of theta. So now we can write down that 2 mgl, the total energy at the bottom, is equal to, and I'm going to expand the brackets of this part here. So I've got mgl minus mgl cos theta plus half mv squared. I'm going to times both sides by 2 and then rearrange to make v the subject. So if I times both sides by 2, I'm going to get 4 mgl equals 2 mgl minus 2 mgl cos theta plus mv squared. I can divide through by m because every term has got m in it, so those m's go, and rearranging I will get v squared is equal to 4 mgl minus 4 gl, because I cancelled out the m, so 4 gl minus 2 gl plus 2 gl cos theta, and that simplifies to give me v squared is equal to 2 gl, it's a 4 gl minus 2 gl, 2 gl plus 2 gl cos theta. I could factorize it if I wanted to. I'm not going to, because this v squared is what I want to substitute here. So now I can write an expression for tension as T equals 2. Then I've got m over L times by v squared, and that is 2gl plus 2gl cos theta plus mg cos theta. Now what's going to happen is these L's will cancel out because I'm dividing by L and then timesing by L. And this simplifies quite nicely actually. T is equal to, right, so here I'll have 2mg here, and then from this other part here I'll have 2mg cos theta plus mg cos theta, so I'll actually have 3mg cos theta, and that's going to be our final expression for the tension. Okay, so let's move on to part B, and we've got a bit of space here. So part B, we need to work out the height of P above A at the instant that the string goes slack. Well, the string is going to go slack when the tension is equal to 0. So we'll just clear off some of this here and then we'll work on part B. So as we said, when the string goes slack, that means T equals 0. So that means that our expression down here is equal to 0. So we've got 2mg plus 3mg cos theta equals 0. We'll divide both sides by mg, so we'll get 2 plus 3 cos theta is equal to 0. We'll take 2 away from both sides and divide by 3, and then we get cos theta is equal to minus 2/3. Now you may remember from the previous part that we said that the height above A, and we needed this for the potential energy, is L minus L cos theta. So you remember it was this green bit here, so L minus L cos theta. Now we know that cos theta is 2/3, so that means we're going to have L minus L times by minus 2/3, which is basically the same as L plus 2/3 L, which gives us 5/3L. So I'll just highlight that and we'll move on to part C. And part C is saying that the maximum height above A reached by P before it starts to fall to the ground again. So what we're going to do now is consider it as a particle moving under projectile motion. So here's our X and here's our Y, and it's going to be moving like this. And what we're going to have is this initial velocity here is going to be this value of V that we worked out. Now we did work out V squared, didn't we? So maybe we can use that here. So we'll just put U, but that U, let's just write it a bit better than that. This U here is going to be equal to the V that we worked out from before. And remember, we had V squared. So we can use that V squared, and that's going to be U. And then the angle of projection, which is going to be this angle here. Now remember, we said that that angle is the same as this angle at the center. Now we know the cosine of that angle is -2/3. So this angle here, we know that the cosine of that angle is -2/3. So we're going to do projectile motion from this point up here. We're going to work out what this maximum height is at this point, but then we need to add it onto the height it's already increased by, which is this 5/3 L. So we know this is 5/3 L, and then we're going to work out how much further has it gone above the 5/3 L at this point here. So we're going to be doing that, and we're going to be doing this taking upwards as positive. So we want to find S, the displacement. Now U is going to be the square root of this, that initial velocity. So it will be a long square root, but you never know, it might get squared in a moment, which will be handy. So it's going to be the square root of 2GL plus 2GL cos theta. We need to be careful actually, because we want to know this vertical component of the velocity. So that's going to be this part here, and this is going to be U sine theta. So that means that this is like the U part sine theta. For the greatest height, we're going to have V equal to 0, and it's moving under the action of gravity. So A is going to be -9.8, seeing as I'm taking upwards as positive. So the equation I'm going to use is V squared equals U squared plus 2AS. Okay, well, V squared is just going to be 0 squared. U squared is going to be all of this squared. So we can get rid of the square root. So that'll be 2GL plus 2GL cos theta, and that's going to get times by sine squared, because we've got to square that as well, sine squared. And we're actually going to work out what sine squared is in a moment. And we can do that by using sine squared plus cos squared is 1. So sine squared theta plus cos squared theta is 1. So we know what cos is, so we can work out cos squared. So sine squared theta is going to be equal to 1 minus cos squared theta. Now cos is -2/3, so it's going to be -2/3 all squared. So that will be 1 minus 4/9, which leaves us with 5/9. So that's what sine squared is. So we can now put those in. So we've got 0 squared in black. 0 squared is going to be equal to 2GL and then plus, now we know what cos theta is, that's negative 2/3. So we're going to multiply this by negative 2/3. So that'll be minus 4/3 GL. And that's going to get times by sine squared, which we said was 5/9. And then I almost forgot, we need to add on our 2as as well, don't we? So we've got u squared there, plus 2as. So 2 times by negative 9.8. So minus 19.6 s. So minus 19.6 s. So now we're just rearranging this to solve it. So I can put 19.6 s. It's going to be equal to, now if I put all of this together and simplify it, I end up with 10 over 27 GL. So from there I can work out S, and that gives me 5/27L. Now remember, that is just the greatest height from this point here, from this point of it leaving a circular path, and I need to add to it this distance here, which is 5/3L. So now the total height, or the highest height, will be the 5/27 plus 5/3L, and that will give me 50/27L, and that will be our answer for part C. Example 20. A smooth hemisphere with radius 5 meters and center O is resting in a fixed position on a horizontal plane with its flat face in contact with the plane. A particle P of mass 4 kg is slightly disturbed from rest at the highest point of the hemisphere. When OP has turned for an angle theta and the particle is still on the surface of the hemisphere, the normal reaction of the sphere on the particle is R. There's some things we need to find, so the first thing we're going to do is to start with a diagram. Okay, so here's my diagram. Particle P is marked. Its initial velocity is 0 because it says that it's disturbed from rest. The velocity at this point I'm just going to call V. Here's the normal reaction. Here's the weight of the particle. We've got the radius of the hemisphere here and the acceleration acting towards the center. This is the angle that it's moved through, theta. So you've got theta here, angle theta. Now, because we have alternate angles here, this angle here is also theta. So we can start with part A. And part A says we need to find an expression for R. So the first thing we're going to do is we're going to resolve forces. And with our forces, we're going to be resolving towards the center of the circle in that direction. Okay, now if I'm going to be resolving towards the center of the circle, I need to know what the component of the weight is acting towards the center of the circle. So I'll just do a slightly bigger diagram up here. So this is the 4G that's here. I've got this angle of theta just here. So that corresponds to this angle here, and there's the 4G. And I want to know what this component is. I'll put the other component in, although I won't need it for this part of the question. I may not need it at all. And I can see that this part here, the bit that I need to resolve towards the center, is going to be 4G cos theta. Right, so resolving towards the center, I have 4G cos theta minus R, which is acting away from the center, equals MA. Mass is 4, and the acceleration is V squared over R, which is 5. I'm going to rearrange that to make R the subject. So I'll have R is equal to 4G cos theta minus 4/5 V squared. Now I'm not finished because I want to use energy to substitute that V squared for another expression. So now I'm going to be looking at the energy. and I'll start by looking at the energy at the top. Now, at that point, the kinetic energy is 0 because it's at rest. Now, to work out the potential energy, I need to pick a point for 0 potential energy. That's going to be the lowest point down here. So that'll be this flat surface. So I'll just mark down here the potential energy here is 0. So that means that for my purposes, the potential energy at the top is m for g and h. The height above the lowest point is 5 meters. So that's 20g. So my total energy at the top is just 20g. So I will just highlight that so I don't lose it amongst my working. So that's the total energy at the top. We're now going to work out the total energy once it's moved for an angle of theta. So the kinetic energy, it's on the move this time, so it's going to be half m4, and its velocity or speed at that point is v squared. So that's the v squared that I've got here. Now the potential energy, it's actually lower than it was. So I'm going to work out what that height is. So that will be 4g times by its height above the center, which is going to be this height here, which is the same actually as this height. So what I'm going to do is draw another little triangle up here so you can see what we're actually working out to work out what h is. So we have this side here, which is 5, and the angle here is theta, so that sort of corresponds to this sort of triangle here, and it's this side here which is going to be the height, which I'm going to be using for potential energy, and I can see that that is 5 cos theta. So that can go into my working. 4g times by 5 cos theta gives me 20g cos theta. So the total energy, once it's moved for an angle of theta, is kinetic energy, which becomes 2v squared, plus 20g cos theta. So I'll just highlight that. Now, by the end, conservation of energy, so by conservation of energy, the total energy doesn't change. So that means the energy at the top, 20g, is going to be equal to the energy once it's moved for an angle of theta, so that's 2v squared plus 20g cos theta. So what I'm going to do now is divide everything by 2, so I've got 10g is equal to v squared plus 10g cos theta. Rearrange it to make cos theta, or sorry, v squared the subject, so that v squared is equal to 10g minus 10g cos theta. Now that is going to go here in this expression. So now I can say that r is equal to 4g cos theta minus 4/5 of v squared, which is this 10g minus 10g cos theta. And we'll see if we can simplify that. I think we can. So we got 4g cos theta. Once we've worked out minus 4/5 of negative 10g cos theta, that will give us plus 8g cos theta here. So plus that to the 4g gives us 12g cos theta. And then we're going to subtract 8g, so minus 8g. So that gives us the normal reaction in terms of theta. So all we need is theta to work out normal reaction. So R equals 12g cos theta minus 8g. I suppose we could factorize it, but I'm going to leave it like that. And I'm going to leave it at the top here because I'm probably going to need it for the next part of the question. And also, I think the expression for v squared down here is going to be useful. So I'm actually going to write that at the top as well. And I'll write v squared is equal to 10g minus 10g cos theta. So we're going to clear the screen and then move on to part B. So part B is asking us to find the angle between OP and the upward vertical when the particle leaves the surface of the hemisphere. And when the particle leaves the surface of the hemisphere, then the normal reaction is going to be equal to 0. So what we'll do is we'll take our expression for the normal reaction and make it equal to 0. So we'll have 12g cos theta minus 8g is equal to 0. We'll divide both sides by 4g, so that we'll have 3 cos theta, not 3g, just 3 cos theta, minus 2 is equal to 0. So from there we can rearrange it so that we get cos theta is equal to, we'll move the 2 across, divide by 3 is 2/3. So then do the cos inverse of 2/3 to find the angle. And on my calculator display I get 48.1896. So I really want an answer to 3 significant figures. So we'll call that 48.2 degrees to 3 significant figures. So let's put that answer up here, 48.2 degrees, and that's 3 significant figures. So what we'll do is we'll clear the screen again so that we're ready for part C. So part C says the distance of the particle from the center of the hemisphere when it hits the ground. Now what's going to happen is that when this angle is about 48.2 degrees, this hemisphere or this particle is going to leave the hemisphere, and then it's going to become a projectile. So we're going to need projectile motion. So if I try and draw roughly what it looks like, so its path is going to be something like this. That's roughly what it's going to look like. But what's important is that we're now going to be using projectile motion at this point here. Now if we're using projectile motion, we need to know its height above the ground when this angle, or the cosine of this angle, is 2/3. And we also need to know the distance from O, because we're going to work out this horizontal distance here. So we'll work out the horizontal distance from projectile motion, and then we'll add it to this distance here. So step number 1, let's work out what these horizontal and vertical distances are from O to P. So I'll just mark a little diagram here, like this. So this is where P is here. This is O, the center of the circle, and I want to find out what these two distances are. Now I know that this angle here is theta, so this matches up to this part of the diagram here. And I also know that this is 5. Now I actually know that the cosine of the angle is 2/3. So I'm going to write these measurements in circles. So the cosine of that angle is 2 here. So these are not the actual lengths of the sides, but the ratio. So 2/3 here. Okay. That means that the length of the side opposite to the angle is going to be the square root of 3 squared minus 2 squared, or the square root of 9 minus 4, which is root 5. So again, this is not the actual length of the side, these are the ratios, so that I can work out sine theta, and sine theta is going to be root 5 over 3. So now I can work out the lengths of the sides. So this side here is going to be 5 cos theta, so write that down, 5 cos theta. So that's basically 5 times by 2/3, which is 10 over 3. So I've got that distance there. And then for the one at the bottom, that's going to be 5 cos theta. So 5 sine theta. 5 sine theta. So that's going to be 5 times by root 5 over 3. Okay, so that is the length of this side. Okay, so let's just highlight those. here, because these are the measurements that I'm interested in. So these are the horizontal and vertical distances of P from the center of the circle. Now we also need to work out the velocity here, and then use that to find out, or the speed at this point, and then we can use that to find out what the horizontal and vertical velocities are at that point. So when it leaves the circle, when r equals 0, we know that the cosine of the angle is 2/3. So that means that v is going to be equal to the square root of this. So that's going to be 10g minus 10g times by cos theta, which is 2/3. So it's the square root of all of that. So v will equal the square root of 10g over 3. So that will be our initial velocity or speed at this point. So I've done a little sketch here because there's a lot going on, and this diagram represents what we've got so far. So down here we've got the center of the circle. This is when particle P becomes a projectile. So this is the horizontal and vertical distance from the center of the circle. This is the sort of path it's going to take, and here's the initial velocity. So with projectile motion, we consider the horizontal and vertical parts of the motion. So we're going to have to work out what the horizontal and vertical parts of this speed are. So another little triangle up here to help us do that. So this line here represents this initial velocity when it becomes a projectile, which is the square root of 10g over 3. This black dotted line here represents this line here going towards the center. So we know this is an angle of theta. We also know that this velocity leaves at a tangent to the circle. So this is a right angle here, which means this angle here is 90 minus theta, which means then that this angle is 90 minus theta. So this angle here is theta. So that allows us now to work out the horizontal and vertical components of the velocity. So the vertical component here is going to be this times by sine theta. Now remember, we worked out sine theta to be root 5 over 3. So we'll just put over here that this is root 10g over 3 times by root 5 over 3. And this component of velocity here is going to be this cos theta, and that's 2/3. So this will be root 10g over 3 times by 2/3. Now I'm just going to make this square root sign a bit bigger because it is the square root of the whole thing here. Same with this. So our next step now is going to look at the velocity vertically. We're going to work out at what time it takes for this particle to drop this distance, then use that time to work out what the horizontal distance is, and then add that to root 5 over 3 to get the total distance here. That's what we're after. So I'll just put a little thing here. This is what we're trying to find the final answer. So soothe out, and we're taking downwards as positive since everything is going down. S, U, V, A, T. So T is what we're trying to find. A is going to be 9.8 because we're taking downwards as positive. U is going to be this part of the velocity. So we'll try and squeeze that in. So the square root of 10g over 3 times by root 5 over 3. And on our calculator, that simplifies to 7 root 30 over 9. That might be just easier to use. And S is going to be 10 over 3. And we're not concerned about V there. So we're going to use S equals ut plus half at squared. So that will become 10 over 3 is equal to u, 7 root 30 over 9, times by t plus half a, well that's going to be 4.9 t squared. Looks like a quadratic, so that will be 4.9 t squared, 4.9 t squared plus 7 root 30 over 9 t minus 10 over 3 equals 0. So we're going to use our calculator to work out the values of t. So we're getting two answers. One is negative. We'll ignore that. That's like negative 1.367. So we know the time can't be negative. But the positive one we get is 0.497628. I'm going to write the whole thing down. 1388. So what we've got here is the time it takes for the projectile to drop 10.3 meters. Now what we're going to do is to work out what this horizontal distance is. Now remember, with horizontal part of a projectile, it's a constant speed, so we can just do speed, distance and time. So to find out horizontal distance, so horizontal, we'll just use speed, distance and time. And just a reminder, so I formed a triangle here. So we're going to multiply this time by this horizontal speed here. So that horizontal distance will be square root of 10g over 3 times by 2/3, that's the horizontal speed, times by this time, this 0.4976, and that gives me 1.8, let's try again, 1.89612 and so on. So that's this distance here. So we need to add it to the 5 root 5 over 3. So I'll just put that down. That's what we're doing here. So plus 5 root 5 over 3. So we're basically just adding on this here to get this distance. And if we do that on our calculators, I get 5.6222901 and so on. I want to give an answer to 3 significant figures, so I'll just put my answer for part C here. So we'll go 5.62 meters, and that's 3 significant figures. So we'll just highlight that final answer. There's lots to do in this question, lots of bits and pieces, and it may be helpful to draw like separate diagrams so you can see exactly what's going on with each part. So you should now be able to do exercise 1E on pages 28 to 30 of the textbook.